question. If you enable DNS over HTTPS in your browser, and your DNS queries are now encrypted, and your ISP can no longer see that you looked up the IP address for a particular website, does that mean your ISP no longer knows what websites you visit? Most people who have read a blog post about DOH, most people who have flipped the toggle in Firefox or Chrome under the assurance that they are now more private, would answer yes. Encrypted DNS means private browsing. That is the entire pitch. That is why the feature exists. That is what makes it feel like a privacy improvement. And it is wrong, in a specific and important way, that I want to walk through carefully, because the gap between what DOH actually protects and what users assume it protects has been one of the cleanest examples of security theater in the modern privacy stack. DOH is not useless. It does protect something, but it does not protect the thing most users install it to protect. And understanding why requires looking at how web connections actually work at the protocol level. When you type a URL into your browser and press enter, several things happen in sequence. First, your browser needs to translate the hostname, like example.com, into an IP address. Because the network does not route packets to hostnames, it routes them to numbers. This translation is DNS, the domain name system. Traditionally, DNS queries travel in the clear as plain text UDP packets over port 53. Your ISP can see every one of these queries, and because they see the hostname you are looking up, they can build a list of every website you visit. That is the privacy problem DOH was designed to solve. DOH wraps the DNS query in an HTTPS request. Instead of a plain text UDP packet going to your ISP's DNS resolver, encrypted HTTPS request goes to a DOH-capable resolver, typically operated by Cloudflare, Google, Quad9, or a similar provider. The query, including the hostname, is encrypted in transit. Your ISP, looking at the network traffic, sees an HTTPS connection to a known DOH endpoint. They cannot see the contents of the query. They cannot see what hostname you looked up. This is where users stop reading and declare victory. Encrypted DNS means private browsing. Problem solved. Here is the problem. The DNS lookup is only the first step. After your browser resolves the hostname, it has to actually connect to the server. That connection happens over IP, and IP packets include destination IP addresses in the clear. Your ISP sees the IP address of the server you connect to, because every router between you and that server needs to see it in order to deliver the packet. You cannot encrypt the destination IP address, because the network fabric itself needs to read it. For a significant majority of the web, that destination IP address is trivially mappable back to the hostname. Cloudflare publishes public ranges. AWS publishes public ranges. Google Cloud, Azure, Fastly, every major CDN and cloud provider has documented IP ranges that correspond to specific properties. A reverse lookup of the IP you connected to, combined with publicly available data about which sites are hosted, on which infrastructure, often reveals the hostname with high confidence. But the bigger leak, the one that makes DOH largely cosmetic for the average user, is SNI, Server Name Indication. When your browser establishes a TLS connection to a web server, part of the TLS handshake involves your browser telling the server which hostname it wants to connect to. This is necessary because many web servers host multiple domains on the same IP address, and the server needs to know which certificate to present. The hostname is sent in a field called Server Name Indication. And in standard TLS 1.2 and older TLS 1.3 deployments, this field is transmitted in the clear before the encrypted portion of the handshake begins. Your ISP, watching the TLS handshake, sees the exact hostname you are connecting to. Not hashed, not encrypted, just the string example.com sitting in a packet readable by anyone on the network path. This is the killer. Even if your DNS is perfectly encrypted with DOH, the very next step, the TLS connection to the server, leaks the hostname in the clear. Your ISP does not need your DNS queries to know what websites you visit. They have SNI. They have always had SNI. They are not reading your DNS to figure out where you go. They are reading your SNI. For most users, enabling DOH moves one piece of information out of ISP visibility and leaves a more informative piece of information in full visibility. The net privacy improvement against an ISP adversary is close to zero. Let me cover the piece of the puzzle that could actually fix this, because it exists, it is deploying now, and it is the missing half of the privacy improvement that DOH was marketed as. ECH, Encrypted Client Hello. This is a TLS extension, standardized in the IETF, that encrypts the SNI field along with the rest of the initial client hello using a public key that the server publishes via DNS. With ECH deployed, your ISP sees an opaque TLS handshake with no hostname leak. Combined with DOH, which encrypts the DNS lookup, ECH is what actually delivers the privacy outcome that DOH alone does not deliver. The problem is that ECH deployment is not yet universal. As of 2025, Cloudflare has enabled ECH by default for all sites behind their infrastructure, which covers a large percentage of the web. Firefox supports ECH in recent versions. Chrome has rolling support. But many websites, many CDNs, and many client environments still do not support it. In mixed environments, your browser falls back to unencrypted SNI, and the privacy hole reopens. The second problem is that even perfect ECH does not fully close the IP address leak. Your ISP still sees that you connected to a specific IP address, and if that IP address hosts a single domain, the host name is effectively revealed. ECH is most effective when combined with large shared infrastructure like CDNs, where many domains sit behind the same IP, so knowing the IP does not narrow down the domain. For small sites on dedicated IPs, ECH provides less protection. The third problem, and this is the one that generalizes beyond DNS and SNI, is that modern web traffic analysis does not need content. It needs metadata, and metadata leaks through multiple channels simultaneously. Packet timing patterns, connection volumes, burst characteristics, and the temporal relationship between outbound and inbound traffic all allow surprisingly accurate site fingerprinting. A 2019 study by researchers at the University of Michigan demonstrated that even with fully encrypted traffic, including ECH, a network observer could identify which specific page within a given website a user was visiting based purely on packet timing patterns, with accuracy often above 90% for popular sites. This brings us to the deeper issue. DOH and ECH together are meaningful improvements over the legacy web. They reduce the casual visibility of browsing activity to passive observers. They raise the effort required for an ISP or a network operator to build a browsing profile. But they do not make your browsing private against a motivated adversary with access to network traffic. And the marketing around DOH specifically has often implied a level of protection that even the full DOH plus ECH combination does not provide against sophisticated adversaries. Let me also address the policy dimension of DOH, because it matters. When you enable DOH in your browser, the default resolver is typically Cloudflare or Google, both of which are operated by companies with enormous visibility into internet traffic. You are not eliminating the ability of a third party to see your DNS queries. You are changing which third party sees them. Your ISP no longer sees them. Cloudflare or Google does. For some threat models, this is a significant improvement because you trust Cloudflare more than you trust Comcast. For other threat models, it is lateral or worse because you now have a single DNS provider with a consolidated view of everyone's DNS queries and no corresponding regulatory relationship with you. There have been concerns raised by network operators, including large corporate IT departments, that centralizing DNS on a handful of DOH providers creates failure modes and surveillance concentration. A DNS outage at a single DOH provider affects a larger fraction of users than a DNS outage at any single ISP. A single subpoena to Cloudflare can reveal more about global browsing patterns than a subpoena to any regional ISP. These are legitimate concerns, even if you accept that for most users, the DOH providers are more trustworthy than the ISPs. Now, the practical guidance. What should you actually do? If your goal is protection against casual ISP observation of your browsing activity, DOH alone is not sufficient. You need ECH as well, which means updated browsers and websites hosted on ECH supporting infrastructure. For sites not yet supporting ECH, a VPN or Tor is the more comprehensive answer because they move the entire TLS handshake, including the SNI, outside the visibility of your local ISP. If your goal is protection against nation-state adversaries or sophisticated traffic analysis, DOH and ECH are both necessary but not sufficient. You need Tor, or equivalent onion routing, which fragments your traffic across multiple relays in a way that breaks the one-to-one mapping between your device and the destination. Even Tor has limitations, and recent research on entry-guard de-anonymization and timing correlation attacks continues to show the edge of what is achievable. If your goal is generic browsing privacy for a casual threat model, DOH alone, as shipped in major browsers, provides a small improvement. Enable it if it is free. Do not believe that enabling it has accomplished much. The marketing framing around DOH has sold users on a privacy improvement that is structurally incomplete without the SNI encryption that DOH alone does not provide. The underlying lesson, which applies well beyond DNS, is that privacy on the internet is not a single toggle. It is a set of overlapping protocols, each of which can leak metadata in different ways, and improving one without improving the others often leaves the overall privacy posture essentially unchanged. DOH fixes one specific leak. SNI, unencrypted at the TLS layer, remains an open window. IP addresses in the routing layer remain visible. Packet timing and volume remain visible. Browser fingerprinting at the application layer remains available. Account logins at the content layer remain identifying. Each layer is its own privacy problem, and closing one layer without closing the others does not close the overall exposure. The right way to think about DOH is as one small piece of a larger puzzle, the rest of which is mostly not solved yet for the general web user. The wrong way to think about DOH is as the privacy solution for browsing, because it is not that, and was never that. Your ISP still sees where you go, not because you failed to enable DOH, but because the protocol that DOH targets is not the primary channel through which your browsing activity leaks. The primary channel is somewhere else, and until ECH is ubiquitous and the other metadata leaks are addressed, that primary channel remains open regardless of what you configure in your DNS settings. Knowing this changes how you evaluate the privacy claims of every tool you install. Ask what specifically it protects against, in precise protocol terms. Ask what it does not protect against. Ask where the residual leakage is. If the answers to those questions are not clear, you have been sold a feeling of privacy rather than the thing itself, and the distinction between those two matters more than any toggle in any settings panel.